The 2023 Nobel Prize went to 3 researchers who saw for the first time how reality works. It is shocking that everything we consider real and genuine is determined by tiny particles moving so fast in a gigantic void that our minds cannot possibly comprehend it. Using light pulses measuring less than a millionth of a second, the award-winning researchers have uncovered a world that could not be more complex, chaotic, and crazy. Despite the apparent disharmony, our world cannot be governed by chance. Even if we think that many things are not right as they are, everything in the subatomic realm seems to be perfectly organized and synchronized. Can we prove our reality in tiny particles and predictable structures? If so, we would have to venture into the world of electrons, neutrons, and protons. In the previous century, German researcher Werner Heisenberg claimed that it was impossible to observe these areas of life. The electrons appeared to behave too irrationally in his research. Heisenberg therefore defined a limit to predictability, measurability, and order, which later went down in the history of natural science and physics as Heisenberg's uncertainty principle. Today, much has changed and new scientific approaches are enabling discoveries that are once again revolutionizing our view of the world. The subatomic realm is where what we see as our reality, as the Earth, as a universe, or even as a tree outside our front door, comes into being. Our bodies are made up of subatomic particles, and every word we speak or every thought we have shapes and moves this world of tiny particles. If we can explore and possibly control this world, or at least understand it first, we may hold the keys to shaping reality in our hands. In 2023, 3 researchers dedicated to exploring the subatomic world were awarded the Nobel Prize by the Swedish Academy of Sciences in Stockholm. Physicists Pierre Agostini, Ferenc Krause, and an Elvier have been working on researching the apparent limits of unpredictability. To do this, they use light pulses in the attosecond range, which flash so briefly that their size is incomprehensible to our minds as the irrational world of electrons. Attosecond flashes of light make electrons go crazy. Put simply, attoseconds are extremely small units of time. Attosecond physics is a new field of physics that aims to shed new light on the world of the smallest particles. If we really want to understand reality, we need to know how this world works. The subatomic realm is the web of matter. It is where all things, all forms, and all phenomena of our lives, including ourselves, originate. If we can find the functions of matter there, the blueprint, then we should also find clues as to who or what builds this world and where aspects such as life, intelligence, and evolution come from. How can attoseconds help here? An attosecond is 1/billionth of a billionth of a second. Numbers like these are difficult for us to imagine, but let's draw a comparison. Within 1 second, as many attoseconds pass as there have been seconds since the universe came into existence. The realm of electrons is determined by these extremely small units of time. Electrons, charged with a negative electric charge, dart around in an incredibly large void and orbit a central point. Together with this point and other particles, electrons form atoms. The movement of electrons also gives atoms a charge and allows them to bind to other atoms, forming molecules. Molecules produce elements, and these build our world. Attosecond flashes can be used to make electrons visible, similar to a particle accelerator. While particle accelerators use collisions with incredible force to make particles observable for a short time shortly after the collision, attoseconds only stimulate the electron for a brief moment. This stimulation causes a change in the behavior of the electrons, and this change provides information about the true nature and physical behavior of the electrons. Atoms, electrons, photons, and other particles are so tiny that researchers could never see them as things or real particles of matter. Even with the best microscopes, they can only observe the effects of these particles and then describe them. When the particles are moving in their natural paths, they are virtually invisible. When researchers apply a deliberate and controlled stimulus, the deviation from the normal path of the particles becomes briefly visible, and with it the nature of the response to the stimulus. From this response, researchers can draw conclusions about the function and elementary behavior of the smallest particles, which in turn allows conclusions to be drawn about the structure of the universe and the forces at work in the subatomic realm. As you can imagine, this is work that requires patience and special technologies. The ultra-short light pulses of attosecond physics exert influence patterns on the subatomic world. Thanks to meticulous measurements made possible by computers, scientists can map the dynamics of electrons and atoms, and these findings have revealed a shocking picture of reality. Nobel Prize winners in LVA, Pierre Agostini, and Ferencvaros, only the best researchers of our time receive the Oscar Science. When the Swedish Academy of Sciences awards its prizes to the world's best researchers each year, it's not only the best in their disciplines who are honored. In most cases, the award also ensures that cutting-edge knowledge, new areas of research, and groundbreaking discoveries are brought to the attention of a wide audience. Before the Nobel Prize was awarded in 2023, probably no one had ever heard of an LVA, Pierre Agostini, and Ferencvaros. After the winners were announced, the three researchers became famous overnight. Each of them has made significant contributions to attosecond physics in their own way. An LVA invented a technique in which infrared laser light is passed through a noble gas, creating an overtone of light radiation in the attosecond range. Pierre Agostini developed a method of serial or trained pulse technology, which he calls rapid reconstruction of attosecond beating by interference of two photon transitions. The researcher generated a sequence of extremely short attosecond trains by passing a strong infrared laser through a noble gas. A further process known as highly harmonic generation produced high-frequency, ultra-short UV pulses. These pulses lasted only about 250 attoseconds each and occurred at such regular intervals that the invention could be successfully used for test series in the field of electron research and imaging. Agostini also used a synchronized laser pulse in his own research to measure the interference between two photon transitions. These interferences enabled him to reconstruct the temporal course of electron motion precisely and with attosecond resolution. His approach made a decisive contribution to the first almost perfect temporal resolution of electron processes in atoms. Ferencvaros was honored for his pioneering work in the generation and measurement of individual attosecond light pulses. The Hungarian-Austrian physicist succeeded for the first time in generating isolated flashes of light that are short enough to capture the movement of electrons in real time. Like his colleagues, he used a strong laser pulse that was sent through a noble gas, generating so-called high-frequency harmonics. The spectral superposition then produced a single attosecond pulse. Using specially developed measurement methods, the researcher was able to determine these pulses so precisely that exact time resolutions in the range of electron movements became possible. Thanks to the work of the three researchers, it became possible for the first time to directly observe the fastest processes in matter. Today, scientists around the world are conducting research with attosecond physics that is revolutionizing our knowledge of the world of elementary particles. Attoseconds shape reality. Let's take a journey into the depths of matter, where our senses have long since failed us but where reality emerges. Thanks to attosecond research, we are gaining insights into this mysterious realm and the fantastic life of electrons. The movements of these particles determine whether an atom binds or not, whether light is absorbed or reflected, whether electricity can flow, or whether a molecule is formed. To do this, they interact in specific patterns, use forces or generate them, build bridges, form bonds or break them down again. All these movements take place on an incredibly short time scale. These tiny movements, performed billions of times per second, turn dead matter into living cells and chaos into order. They create everything that exists out of nothing. And it is the great challenge of research to find out where these processes come from and whether they are intelligently controlled. The attosecond is a unit of time at which our universe is constructed in real time. Those who understand this time scale not only see how the world is, but also how it's literally created out of nothing. If we gain knowledge and control over this dimension, we can begin to not only observe reality but also shape it to a certain extent. By using targeted light pulses, electron trajectories could be influenced, which would mean, for example, that chemical reactions would no longer have to occur purely spontaneously but could be controlled. Initial approaches have already shown that molecules can be steered in their behavior if they are hit at the right attosecond moment. This is a direct intervention in the formation of matter itself. Technologies that still sound like science fiction today could soon become reality. The manipulations could be used to manufacture new materials, control biological processes, or develop ultra-fast quantum computers. The biggest challenge at the moment is still precision. In these incredibly small units of time, any disturbance or even the slightest noise can tip the balance into unpredictable chaos. We need to understand these mechanisms even better if we no longer want to accept reality as a given but want to actively shape it. Research such as attosecond physics takes us a boundary between science and metaphysics. For what happens when we can not only observe but also decide when something happens or whether it happens at all? We become creators on another level of reality, and thus in a sense what religion calls God. The moment an electron changes its state is a creative process that directly influences the reality we see and experience every day. In addition to sincere research in this area, we must remember that technologies and manipulations like these can also become weapons in the wrong hands. Subscribe to the channel now and enjoy many more exciting videos.